Hello, Professor. We could start.
Okay, thank you. Let us start. We are proving the classification theorem for simple spherical varieties, which says, let me recall that the classification theorem states that, roughly speaking, simple spherical varieties containing a given spherical homogeneous space as the open orbit are in a one-to-one correspondence with the colored cones in the vector space spanned by the dual of the weight lattice. And the correspondence is given by associating to a simple spherical variety X with the unique closed orbit Y, its colored cone, denoted like this, which is, again, roughly speaking, spanned by all vectors corresponding to B-stable prime divisors on X. So we have already proved injectivity of this correspondence. And it remains to prove the surjectivity. In other words, given a colored cone, say C, comma B, where C is the cone in this vector space, a cone in this vector space which is pointed and whose interior whose relative interior intersects the evaluation cone, and B is a subset of colors. So given a colored cone, we have to construct a simple spherical variety X with the unique closed orbit Y. Okay, let me maybe put it on the next line to have more space. Excuse me. We have to construct a simple spherical variety X with the closed orbit Y, such that the colored cone corresponding to this X is exactly this colored cone C comma B. So C equals C sub Y, and D over Y equals B. So this is our aim, to prove the surjectivity of this correspondence. Let us first note that the dual cone to the cone C, the cone C check, is a solid, that is full dimensional polyhedral cone. C check is solid because C is pointed. So the cones dual to pointed cones are solid cones and vice versa. This is an elementary exercise in convex geometry. And also, since C is polyhedral, that is generated by finitely many vectors, then the dual cone is also polyhedral. It is again from convex geometry. Now let's consider all lattice vectors in this dual cone C check. They form an additive semigroup. Well, let me draw it on the picture. So suppose you have this cone C check, something like this. For instance, let it be in dimension 2, just for an example. So this is one ray of this cone. This is another ray. Something like this. So this is my cone C. C check, I'm sorry. This is my cone C check. And let me mark by dots the lattice points in this cone. So this, 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 here, 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 and so on. So something like this. Okay. Now there is a well-known lemma in convex geometry, which is called Gordon's lemma, the Gordon lemma. Which says that this semigroup is finitely generated. So the additive semigroup C check intersect with lambda, the semigroup of all lattice vectors in the dual cone C check. This semigroup is finitely generated.
Well, this lemma apply to only solid cone or average?
No. Actually, yes. Thank you. This is a good remark. This lemma applies to any polyhedral cone, any finitely generated cone in a vector space over rational numbers. So it applies in this generality. So for any finitely generated rational cone in a rational vector space, the semigroup of lattice vectors in this cone is finitely generated. But we need this lemma only in this situation. So for simplicity, I formulate this lemma for the cone C check. This is all we need. Okay. So actually, this lemma is quite standard, and I could even omit the proof, referring you to some books in convex geometry. But the proof is very easy. So let me give you a proof for your convenience. So what is the proof of this lemma? Since C check is a polyhedral cone, it is generated by finitely many vectors as a cone. It is finitely generated by finitely many vectors, say lambda 1, etc., lambda k. So this lambda j's are lattice vectors. We may assume that lambda j's are lattice vectors because we work in a rational vector space, and this means that every vector, for any vector, some positive multiple of it is a lattice vector. Okay, so this cone is generated by finitely many lattice vectors, and precisely this means that it is the set of all positive linear combinations of these vectors. So the sum over j's C sub j lambda sub j, where Cj's are non-negative rational numbers. Okay? So maybe it would be instructive to draw these vectors on the picture. For instance, on the picture, we have this vector. Maybe I should draw it better like this. We have this vector, one of the generators. Do it a bit better, like this. And this vector, this is another generator. So these are the vectors lambda 1, etc., lambda k. And now let's consider a set of all linear combinations of lambda 1, lambda k of this form, but with coefficients ranging from 0 to 1. So let me turn to the next page. Let's define a subset, say K, which is the set of all these linear combinations, sum over J, Cj lambda J, such that Cj's, the coefficients range from 0 to 1 and are even smaller than 1. We can consider such a set. This set, this is a subset in my cone, in C check, and this set is bounded. So this set is bounded in the vector space. So let me write it like this. So this cone C check sits in the vector space E star, spanned by the weight lattice lambda. And this set is a bounded subset of this vector space because it consists of linear combinations of a finite set of vectors with bounded coefficients. So this is a bounded subset. And since it is a bounded subset, its intersection with the lattice lambda is finite. So this implies that the intersection of this subset K with the lattice lambda is finite. So it consists of finitely many lattice vectors. Let me continue the enumeration. We had lambda 1, lambda k, and now we have lambda k plus 1, etc. Lambda n. This is a finite set. And clearly, the semigroup of lattice vectors in the cone C check is generated by all these vectors first you have to take lambda 1, etc., lambda k, and then you have to add these vectors in the finite subset, in the bounded subset K, big K, lambda K plus 1, etc., lambda n. So why it is so? Why this semigroup is generated by these vectors? Just look at the picture, or maybe not at the picture, look at the definition of this cone C, of this cone spanned by lambda 1, lambda k. So every vector in this cone is a linear combination with lambda j's, where j is ranging from 1 to k, a linear combination with non-negative coefficients. So if you subtract if you subtract some positive integer from Cj, you will obtain a number in the segment from 0 to 1, right? Just you subtract the floor of Cj, the largest integer less or equal than Cj from Cj. You will if you subtract this integer number from Cj, you will obtain the coefficient in this range. And when you subtract this integer from Cj, you subtract some multiple of lambda j, some integer multiple of lambda j from this vector. And you get into this subset. And all this subset, we include these vectors in the generators. So every vector in C check, which is integer, which is the lattice vector, can be obtained from some of these vectors by adding lambda 1, lambda k with positive integer multiples. And this is exactly what is claimed here, that this semigroup is generated by this set of vectors. For instance, on the picture, let me draw this on the picture. So on the picture, we have this set K given by the following. So you have to take, I think, you have to take this area. Yeah. So this is K. Excuse me. This is K. And now you take the generators of your cone, that is lambda 1, lambda k. So let me indicate these generators by red dots. And you add all lattice vectors sitting in this set K. These are these red dots, which I indicate now. This, and this. I don't take this vector because I assume that my subset K is defined by these inequalities, where here we have a strict inequality. Okay, and now I claim that the vectors marked by red dots are exactly the generators of this semigroup of lattice vectors in the cone. Okay, so this proves the Gordon lemma. This proves the Gordon lemma. And now let's go on. So let's fix the generators of the semigroup of lattice vectors in my cone C check. I will denote it like in the proof of Gordon's lemma by lambda 1, etc., lambda n. These are the generators of C check intersect with lambda. And the respective semi-invariant functions f lambda 1, etc., f lambda n, semi-invariant functions, semi-invariant rational functions on the spherical homogeneous space Y naught, whose embedding we have to construct. These semi-invariant functions may have poles on this spherical homogeneous space Y naught only along the divisors sitting in the, only along the colors sitting in the complement of the subset B. Let me denote this set of colors as D1, etc. dt. Well, just because these eigenweights, lambda 1, lambda n, sit in the cone C check, and this means that the vectors corresponding to the divisors in D, in B, the vectors corresponding to the colors in B, these vectors are among the generators of C check. These vectors have non-negative pairings, with these weights lambda 1, lambda n. And since the pairing is non-negative, this means that the vanishing order of each of these functions along each of the divisors in B is non-negative. So f lambda j cannot have a pole at the divisor in D. Okay? So maybe let me write some comment here, because the vanishing order of each of these functions f lambda j along any color in B, which is equal to the pairing vd bar comma lambda j, is non-negative, for any D in B, just because these vectors vd bar are in the cone C check. Okay, so so all poles of these functions f lambda 1, f lambda n, are in this set of divisors. Okay, and now let's take a divisor on y naught, which is the sum of this d1 dt with sufficiently big coefficients. So take the divisor delta equal to m dot d1 plus etc. plus dt, where m is big enough such that, well, first we want to have that the line bundle corresponding to this divisor, the line bundle over y naught corresponding to this divisor, carries on the action of G itself. So we know that the action of G on y naught can be lifted to the action of some finite cover of G on the total space of the line bundle. But if we replace this line bundle by a sufficiently big power, that is, if we replace the respective divisor by a sufficiently big multiple, then actually the group G itself, the action of the group G itself, is lifted to the total space of L. And we want to assume this. And also we want to take M big enough such that the vanishing order of all these functions f lambda 1, f lambda n, along all the divisors d1, dt, so the vanishing order of f lambda j along I, is greater or equal than minus m for any I and j ranging in the respective range. So this is possible because we have finitely many functions f lambda 1, f lambda n, and finitely many divisors d1, dt. And we know that these functions may have poles along these divisors, but since there are finitely many of them, the vanishing order at poles is bounded from below. So we take m big enough so that the vanishing order of all these functions is greater than minus m. Okay. Now, yeah, any question? No. Okay. So now under this choice, observe that if we take the canonical B semi-invariant section of the line bundle L corresponding to the divisor delta, so let me denote this section by S naught. S naught is the canonical section of my line bundle L. It is B semi-invariant, and the divisor of this section S naught is exactly delta. We have such a canonical section of the line bundle corresponding to a divisor. Then, if you take this S naught, and if we multiply this S naught by all these functions f lambda 1, f lambda n, then we get sections Sj. So Sj is by definition f lambda j times S naught. And this section is again regular. It has no poles. Because the poles may come from the poles may come from the poles of these functions f lambda j, but since the vanishing order of each of these functions along each of these divisors is greater or equal than minus m, and the section S naught has a zero of order m along this divisor di because of this form of the divisor delta. So the section S naught has zeros of order m at each of these divisors. So these zeros of the section S naught kill the poles of the function f lambda j, and we get a regular section. For any j ranging from 1 to n. We have a bunch of B semi-invariant. Again, this section is B semi-invariant because both vectors here are B semi-invariant. So we have this bunch of B semi-invariant regular sections of the line bundle L. And now we can generate simple G submodules by these semi-invariant sections. So these semi-invariant sections, Sj, are highest weight vectors of simple G submodules in the space of sections. So we get these simple G submodules. Let me denote them by M sub j. It is just the linear span of the G orbit of each of these sections Sj. It is a simple G submodule. Okay, and the highest weights of these simple submodules are pairwise distinct because the highest weights of all these Sj's, the weights of all these Sj's are pairwise distinct, since they are obtained from the weight of S naught by adding pairwise distinct weights lambda j. So all eigenweights of these Sj's are pairwise distinct, and therefore we have distinct simple G submodules in the space of sections, pairwise non-isomorphic simple G submodules in the space of sections, and we may take the direct sum of all of them. So let M denote the direct sum of all these simple submodules starting from M0.
Well, why is Mj simple?
Because it is generated by a highest weight vector. This is just from representation theory of G. So if you have
S naught, I don't think S naught is highest weight.
It is because it is semi-invariant, B semi-invariant. And this is because its divisor is B stable. Okay? The divisor is B stable, therefore the section is B semi-invariant. We have discussed this point some time ago at some of previous lectures. So if the divisor is B stable, then the section is B semi-invariant. Okay? Okay, so we have this finite dimensional G submodule in the space of sections of my line bundle L over Y naught. And this gives rise to a G-equivariant map, as we know. This gives rise to a G-equivariant map, let me denote it by phi, from this homogeneous space Y naught to the projectivization of the dual vector space M star.
Well, what is M naught?
M naught is
spanned by S naught, right?
Exactly. So this notation holds for all J starting from 0. And for S naught, it works as well. Okay, so we have this G-equivariant morphism from the spherical homogeneous space Y naught to the projectivization of the dual module M star, given, well, so we have discussed how a finite subspace of sections defines such a map. And now the construction of a simple spherical embedding is as follows. So let me present the construction. The construction is as follows. So let me draw it on the next line. Okay. So let me denote by X bar the closure of the image of this map.
So
in the projective space, yes.
No, not quite that. So
far it's okay.
Well,
okay.
So we use that simple G module are finite dimensional, right?
Yes, of course. We use this, and so we use that. Actually, I told you some time ago that there is a general fact that if you have
yes, I know that there is a finite dimensional invariant subspace. No, I remember.
Yes. So so I do not mention this explicitly, but I assume that we already discussed these things, and now I just use them without further mentioning. Okay, so the construction is as follows. So first, let's denote by X bar the closure of the image of the homogeneous space Y naught under this map to the projective space P of M star. Then let me denote by X upper naught and affine open subset in X bar. So this X bar is by definition this closure, and X naught is a finite and affine open subset of X bar obtained by removing the hyperplane section. So we remove the vanishing locus of S naught. So we remove this hyperplane section from X bar, and we get an affine B-stable open subset. It is affine and B-stable because S naught is B semi-invariant. And finally, so maybe I should write it some here. So this is projective spherical G variety, projective spherical variety. And this guy is affine B-stable open subvariety. And finally, we define X to be the G-span of X naught. So X is an open subvariety in X bar, an open G-stable subvariety in X bar, and X will be our simple embedding of Y naught. This is the construction. We want to prove that X is indeed a simple embedding of Y naught, and the colored cone of X is the one we started with, the colored cones C, B. We'll do it in several steps. So now we want, let me repeat, now we want to prove that this X we just defined solves our problem. So this X is this guy. So it is a simple spherical embedding of Y naught, such that its colored cone is exactly the colored cone C, B. Okay. Let's make the first step. We have this projective variety X bar. We may consider the affine cone over this X bar, and we consider the coordinate algebra of this affine cone. So we have X bar hat. This is the affine cone over X bar, and its coordinate algebra can be identified with the subalgebra in the direct sum of all sections of the positive powers of L the direct sum over D ranging from 0 to infinity. The coordinate algebra of X bar hat can be identified with a subalgebra in this big algebra of sections. Subalgebra generated by the space M. So the elements of this coordinate algebra are, well, the homogeneous. This is a graded subalgebra. The homogeneous elements of this subalgebra are exactly the homogeneous forms, the homogeneous polynomials generated by vectors in M. So you may take a basis of M. This will be the basis vectors will be the coordinate functions, the projective coordinates on this projective space. And we consider homogeneous polynomials, homogeneous forms in these projective coordinates. And this is exactly, this exactly gives you this algebra. Okay? And the coordinate algebra of the affine open subset X naught, which we just defined, is identified with the subalgebra in the field of rational functions over Y naught. Subalgebra generated by M over S naught. So when we consider this affine chart given by removing the hyperplane section, the vanishing locus of S naught, on this affine chart, the affine coordinates are obtained from projective coordinates, that is basis elements of M, by dividing over S naught. And the subalgebra generated by these functions is exactly the coordinate algebra of X naught. Okay?
Dividing, the dividing is the function, is in the function sense, right?
This is yes. So we divide. We take a ratio of two sections from one and the same space of sections, from the space of sections of L, and the ratio of these two sections gives you a function, generally a rational function with poles in the set of poles of S naught. But we remove these poles, and therefore we get a regular function on X naught. So each regular function of X naught is generated by functions like this, by affine coordinates. Okay? now let's denote, let's recall that my colored cone is generated by the set B, the set of colors B, and finitely many vectors in the evaluation cone. And let's denote by, say, V1, etc., VR. Let's denote the generators of extremal rays of the cone C, which do not contain colors, which do not contain vectors corresponding to colors from the set B. And since the cone C is generated by these vectors and finitely many vectors from the evaluation cone, so if you take the generators of the remaining extremal rays which do not contain these vectors, then these generators have to be in the evaluation cone. So these vectors actually sit in the evaluation cone. Now we want to prove the following claim. Maybe let me turn to the next page. We want to prove the following claim. That actually
the last page about something I did not.
Mm-hmm.
The extremal rays of C.
Yeah.
And does not belong to. Oh, this is a characteristic of a colored cone.
Well, what is the colored cone? The colored cone, this by definition of the colored cone, this cone C is generated by all these vectors and finitely many vectors from the evaluation cone. So each extremal ray of this cone has to contain one of these generators. If it does not contain these vectors, then it has to contain vectors from the evaluation cone V. Okay, because there are no other generators. Some of the extremal rays contain these vectors, and the remaining extremal rays have to contain vectors from the evaluation cone, which are among the generators of C. Okay?
Well, C generated by V1 up to VR and VD bar, right? Yes, I know.
Yes,
I know that.
yes.
But why the extremal rays should be generated by elements in V?
Well, if a convex cone is generated by finitely many vectors, then each of the extremal rays,
the extremal rays must be generated by a base
by one of these generators. Yes. Okay.
Well, they are the extremal rays that does not generated by VD bar, right?
Yes. We take these extremal rays which are not generated by VD bars, and therefore they have to be generated by some vectors from here. Okay. Well, let me go back to the claim. The claim is that the coordinate algebra of this affine open subset X0 can be described as follows. It consists of all functions which are regular on the open B orbit. The open B orbit we denoted by Y upper node, if you remember. So this means that a function f has a B-stable divisor of poles. So f has B-stable poles. It is everywhere defined on the open B orbit, and therefore the poles are in the complement of the open B orbit. The poles are B-stable. Okay? So the coordinate algebra of X0 contains of all functions with B-stable poles, such that the valuations corresponding to the vectors, v1, vr, and all these vectors, the valuations corresponding to all these vectors take non-negative values on f. So the inequalities are that vi of f greater or equal than 0 for any I from 1 to r, and also vd of f greater or equal than 0 for any d in the set B. So this is another description. Of the coordinate algebra of this open subset X0. Okay. We have already seen that this algebra is generated by, as a subalgebra in the field of rational functions, it is generated by this space. But we can describe this algebra differently by this formula. Let me prove the claim.
We'll find the logarithm from y0 to the projective space is an embedding, right?
This is an embedding, but so far we didn't prove it. Yes, you are right. This map will appear to be an embedding, but we didn't prove it yet. So far we didn't prove it.
If we don't prove it, then how can we deduce that kx upper node, the regular function on x upper node, is contained in the function field?
Well, just because this map phi is a dominant map, to x bar, so phi maps y0 to x bar dominantly, and this means that the pullback of functions is an embedding. So this inclusion is given by the pullback of functions. It is an embedding since this map is dominant onto its image. Okay.
Oh, dominant does not
yes.
need to be embedding, just dominant.
So far, yeah, it will appear to be an embedding. We shall prove it, but so far we don't know it. So far we only can say that it is a dominant map, and the inverse map of functions, the pullback map, is embedding. Is an embedding. Okay. Maybe for your convenience, I should write this sign here. So it is an embedding given by the pullback, and also here. Okay, so let's prove this claim. I see that the first half of my lecture. Well, maybe before proving this claim, let me also indicate a particular case of this claim. So in particular, it will follow from this claim, in particular, it will follow from this claim that a semi-invariant function f sub lambda is regular over x0 if and only if its eigenweight lambda sits in the dual cone C check. It is a lattice vector in the dual cone. This is just because these inequalities defining the coordinate algebra of x0, if you substitute f lambda in here, then you get that the pairing of lambda with the respective vectors will be non-negative. The pairing of lambda with vi and vd bar will be non-negative. And this exactly means that lambda is in the dual cone. So we have the description of eigenweights of all semi-invariant functions sitting in this coordinate algebra in terms of lattice vectors of the dual cone. Okay. Well, now let me.
So the regular function on x0 contained in the regular function on y0.
X. Yes. Of course.
It's still given by the pullback. right?
Yes. So all the inclusions are given by pullbacks. I just don't want to write this pullback map to make notation simpler, but all these inclusions are given by pullbacks. Well, now I see that maybe I should postpone the proof of the whole claim to the second half of my lecture. So let me stop here and have a 10 minutes break. If you have questions, then I'm ready to answer as usual.
Well, the image of y upper knot is inside x upper knot, right?
The image of y upper knot is inside x upper knot just because if you take any point on y upper knot, then all how to say then any semi-invariant function or any semi-invariant section of the line bundle does not vanish on this y upper knot because it is semi-invariant and y upper knot is an open B orbit. So all semi-invariant functions, all semi-invariant sections do not vanish here. And what is x upper knot? It is obtained from x bar by removing the vanishing locus of S naught. S naught is B semi-invariant. When you remove its vanishing locus, then of course you do not touch y upper knot because S naught does not vanish at any point of y upper knot. Okay? So indeed, this means that y upper knot is contained in x upper knot. More questions?
What I did not listen clearly about why the image of y upper knot is inside x upper knot. I mean y upper knot is the open B orbit in y naught, right?
Well, let me maybe write a bit more. I write it temporarily. After that, I will erase it. But anyway, so let me observe that S naught is B semi-invariant, and this implies that S naught nowhere vanishes on y upper knot. Is it clear? Because y upper knot is a B orbit, it is an open B orbit, and S naught is a B semi-invariant section. If it vanishes at some point in y upper knot, it vanishes identically on y upper knot because it is B semi-invariant, and it is a single B orbit. But if it vanishes identically on y upper knot, it is just a zero section because it is dense. Y upper knot is dense in y lower knot, and therefore we get a contradiction because S naught was chosen to be a non-zero section.
I know. Thanks.
Okay, and so if this holds, this implies that phi of y upper knot is contained in the non-vanishing locus of S naught. And the non-vanishing locus of S naught intersect with x bar is exactly x naught. So x naught is exactly x bar intersect with this non-vanishing locus. Okay? That's why phi of upper knot is contained in x upper knot. More questions? Okay, I'll switch off my microphone for the rest of the break. But if any questions come to your mind, then just ask me, because I'm here. I will switch on and answer your questions. Okay, let's continue with the proof of this claim. So we have to prove two inclusions from the left-hand side of this equality to the right-hand side and vice versa. So let's start with the first inclusion. let's prove that the coordinate algebra of x naught is contained in the right hand side. So we prove this inclusion. Well, the coordinate algebra of x upper naught is generated by the functions of the following form. So f equals to s over s naught, where s sits in the subspace M. If f is such a function, then first we can say that f is regular on the open B orbit, just because the numerator of this fraction, the section S, is regular everywhere on the G orbit, y lower naught, and S naught, the zeros of S naught are bistable. The zeros of S naught are in this set D1, etc., dt. These are bistable divisors, and therefore this fraction is has no poles on the open B orbit. And also the vanishing order of this function f at any d, at any prime divisor d in the set of colors B is non-negative. Well, let me say like this. This is because excuse me. Let me say like this. Since the section S is regular, then for any D in B, the vanishing order of the section S along D is non-negative. That just because the section S is globally regular, is everywhere defined. And since the denominator of this fraction has zeros only along the colors in the complement of D, then the function f, this ratio, has no poles along D, has no poles along D, and therefore this inequality also holds. Okay. Now it remains to check these inequalities. And this is done as follows. So first observe that if we extend any G invariant valuation to the bigger field, to the fraction field of this algebra of sections, for instance, if we extend any G invariant valuation to the fraction field of this algebra of sections, or even to the fraction field of this coordinate algebra, to the field of rational functions over the affine cone over x hat, over x bar, then we may speak about the values of G invariant valuations at sections of the line bundle L, at here and here. So observe that the section S belongs to the space M, and this space M is the direct sum of simple G submodules M0, M1, Mn. And we know how to compute the invariant valuation on the function in terms of its projections to simple G submodules. So we get the formula that the value of Vi, of each of the valuations Vi at the section S, is greater or equal then the minimum of the values of Vi over all sections Sj. These sections are highest weight vectors in these simple submodules. We also know that the value of a G-invariant valuation on any simple G module in the space of functions or sections on which we compute the valuations.
So how can we define a valuation on the space of sections?
Well, some time ago we discussed that we can extend a G-invariant valuation from a given field to a bigger field. There were some lemmas, maybe 2 or 3 lectures ago, about extension of G-invariant valuations. We have discussed this kind of things there. Okay?
Oh, well, I have to.
Yeah. Just look at your notes or at the notes on the disk. We have discussed this kind of things when we discussed G-invariant valuations. There was an extension lemma that any G.
We extend to the
So we have evaluation. So let me just say
the bigger field is generated by quotients of sections, right?
We have evaluation on this field. Yeah, we have evaluation on this field.
Yes.
Therefore, we have evaluation on the smaller field, on the field of functions of x bar, say, if you like, because and we can extend the evaluation from the field of function of x bar to the field of functions of x bar hat. Because we have a projection map from here to here.
I mean, I know.
Okay, so this kind of things. Well, we have this inequality. So the value of Vi over at S is greater or equal than the minimum of values of Vi at all these sections Sj, generating the simple submodules here. So let me explain a bit more. So S sits in here, S sits in M. And the value of Vi at S is the minimum of values of the projections of S to these summons. But the value of Vi at each of these summons is constant. This we also discussed when we discussed G-invariant valuations. So the value of Vi at each of these projections is the same as the value of Vi at Sj, the generator of this simple module. But of course, not all of these projections have to be non-zero. Therefore, we have to take only those projections which are non-zero. And therefore, here, we have to take not all Sj's, but only those for which the projection of S to the respective simple submodule is non-zero. That's why if we take all Sj's here, then we have the minimum may be smaller. So we have an inequality here, but it is sufficient for our purposes. So we have this inequality, and this implies that the value of Vi at F, so F is this fraction, the value of Vi at F is greater or equal than the minimum of values of Vi at the fractions Sj over S naught. And these fractions are exactly the functions f lambda 1, f lambda n, because of how we define these sections. So Sj is f lambda j times S naught. That means f lambda j is Sj over S naught. So maybe I should write here that this guy is exactly f lambda j. And therefore, this minimum is exactly the minimum over J of all pairings Vi with lambda J. Okay? But this is, let me move it a bit to the left. But this is non-negative. Just because lambda j's are in the cone C, in the cone C check, and Vj's are in the cone C. So here we have pairings of the vectors from the cone C with the vectors from the dual cone, and all these pairings are non-negative. So we have proved these inequalities. And we conclude, hence, we conclude that F sits in the right-hand side of this formula, sits in this set of functions. Okay? And more generally, so we have proved this for the function f of this form. But if you take any function in the coordinate algebra of x naught, it has the following form. So more generally, if you have a function in the product space m over s naught times m over s naught times etc. times m over s naught, then still we have that f is regular on y naught, on y upper naught, on the open B orbit, just because all factors in this decomposition are regular, as we have proved, all factors in this decomposition are regular on y upper naught. And also, from the multiplicative property of the valuation, we see that the values of all VDs at F are non-negative, and the values of all VIs at F are non-negative for any I from 1 to R. Just because these inequalities hold for the factors in this decomposition, and the evaluation is a multiplicative function. It takes a product to a sum. It is a homomorphism to the additive group of rational numbers. So this means that for any function of this form in this product space, these conditions hold true. But these functions generate the coordinate algebra of x naught. So,
hey, Professor, I have a question.
Yes. Mm-hmm.
So, in this proof of the right inclusion or left inclusion, we can see that the valuation of f at vi is non-negative even for every vi inside the dual cone C check.
Exactly. Exactly. Yeah.
So
yeah.
Why we use the extremal rays?
That's because we have to use these inequalities for finitely many vectors. We will need finiteness. So we want to have finitely many inequalities here. This is a good question. You are absolutely right that actually this will hold true for any vector corresponding for any vector in the cone C, which sits in the evaluation cone. So in the intersection of C with the evaluation cone. And we, by the way, we shall use this sometime later in the proof. But why I use only VIs here? Because I want to have finitely many inequalities. This is my reason. I want to have finitely many inequalities.
So
but
because the extremal rays generate the whole cone, so
well, I mean, this is a bit more tricky because I would say you can deduce this inequality for any v in C. For any v in C intersect with big V. You can deduce this inequality for any v from these inequalities if your function f is B semi-invariant. Because this just then says that if you have a pairing of lambda with all these vi's greater or equal than 0, so if you have this pairing, well, with lambda here greater or equal than 0, then you have the pairing with v also greater or equal than 0. But these arguments works only for B semi-invariant functions. For general functions, it is a bit more complicated because you cannot just, so when you compute G-invariant valuations on arbitrary functions, it is more delicate. But this is true. What you have said, this is true. And I hope you will see maybe even today in the course of the proof where we use this finiteness. Well, let me write the conclusion that we have deduced that hence we have deduced that any function in this coordinate algebra sits in the right hand side. So we have deduced that the coordinate algebra of x0 is contained in the right hand side. Okay, and now let's turn to the reverse inclusion. Now we have to prove this inclusion. Well, how we do this? Let's take any function. Let's take any function in the right-hand side. Any function which is regular on y0 and which satisfies these finitely many inequalities for valuations. Okay, so we have this function f, which is regular on y upper node on the open B orbit. And also, it has no poles along colors in this subset B. This is this condition. Then this function f may have poles on my spherical homogeneous space y0 only along the divisors, the colors in the complement of B, only along these colors d1, etc., dt. So you have a function which is regular everywhere outside these divisors. And this means that this function can be represented as a fraction big F over S0 to the power D for some regular section big F of some tensor power of my line bundle L with D sufficiently big. Because when you recall that this section S0, has zeros only along d1 dt, only along these divisors, and the order, the vanishing order of S0 along these divisors d1 dt is m, is a positive number m. So if you take S naught to a sufficiently big power, then the vanishing order of S naught along this divisor d1 dt will be as big as we want. Will be as big as we want. And if we multiply my function f small by this S naught to the power d, then we will kill the poles of the function f, because the vanishing order.
So we choose d so that md is larger than the the absolute order of f on di, right?
Exactly. We choose d big enough so that multiplying with S naught to the power d will kill the poles of f. Yes, and therefore we get a regular section of this tensor power bundle. So we can represent this f in this form. Okay, and now we can decompose this section. So the section big F can be decomposed as the sum of its projections to irreducible G submodules. So the sum over some k of fk's, where fk is a non-zero projection to an irreducible submodule of the space of sections, the irreducible submodule of some highest weight mu k. This is my notation for irreducible submodules in the algebra of functions or sections or whatever. I already used it before. So these are the non-zero projections to irreducible summands in the space of sections. And then we know how to compute the values of G-invariant valuations. So each of these VIs, if we extend it to the space of sections, as we explained before, we can extend a G-invariant valuation to a bigger field. Each of these VIs, its value at F is equal to the minimum. Here it is equal because we take only non-zero projections, is equal to the minimum over K of the values at these projections Fk's. And this value is the same. This value is the same as the value. So again, minimum over k, the values at highest weight vectors in this irreducible submodule. So let me denote by f mu k. So f mu k f mu k is the highest weight vector, in this space in this irreducible submodule of the space of sections. So it sits in the space of eigenvectors in the space of sections. Eigenvectors for B with eigenweight mu k. Okay.
Professor, the extension of VI only happens on the subalgebra generated by M. How can it?
Well, you can extend. I said that you can extend even to this, even to this algebra, to this one. It is no problem to extend to a coordinate to any bigger field. So we can extend to this field, but we also can extend to the fraction field of this algebra. Okay. Actually, the fraction field will be the same. Well, it requires some explanation, but I don't want to go deep into this because I don't need this in detail. So both these two algebras, this one and this one, have one and the same fraction field. You can try to prove it as an exercise if you like. But even if it were not so, then we could extend the valuation to the fraction field of this algebra. Okay. Let's go on. This implies this computation for the values of vi at f implies, well, let me write like this. Let me denote. Let me continue the fractions f mu k over s naught to the power d. These are already functions, and these are semi-invariant functions of some weights, say mu k. These are semi-invariant functions, semi-invariant rational functions on our homogeneous space of some eigenweights nu k. And what we have just computed implies that the pairing of vi with each of these weights nu k, it is the same as the value of vi at f nu k is greater or equal than the value of vi at f, because f is given by this fraction. So the value at f is the difference of the value at big F and the value at the denominator. But the value of big F is smaller, is the value at big F. So what I want to say, yeah, the value at big F is the minimum of these values at f case. And if we subtract the value of the denominator, we get the value at this fraction. So it will be, so the minimum of these values, will be exactly this guy, the value at f.
So f nu k is we did not talk about the pole of f nu k, right?
F nu k has poles only in here. The same argument as for f. F nu k has the poles only in here because the numerator is a regular section. It is a regular section. The numerator has no poles at all, and the denominator has zeros only in here. Therefore, f nu k has poles only in here. Okay? By the way, it is a good remark, but let me first say that by this computation above, we have this estimate from below. So the value of the value of vi at f nu k is greater or equal than the value of vi at f, which is non-negative because the function f was taken from this set. So we have these inequalities here, okay? And also what you have just said, let me reformulate it like this. The pairing of Vd bar with nu k, it is the same as the value of Vd, the evaluation Vd f at f nu k. It is also non-negative because what I just have said, because the function f nu k has poles only along these divisors, may have poles only along these divisors. So for any d in the complementary set,
can we deduce that nu k is a highest weight? I don't think the quotient of two highest weight vector is the highest weight vector. The product,
well, it is, let me say, it is not a highest weight vector. It is a B semi-invariant rational function. Because the representation in rational functions is not as good as the representation in regular functions or in sections. There is no finiteness theorem that any vector is contained in a finite dimensional G submodule and so on. So the representation in rational functions is not so good, and so we cannot speak about highest weight vectors there. But we can say that this function is B semi-invariant. because it is a ratio of two Bessemer invariant sections. When you act by B, the numerator is multiplied by some weight, and the denominator is multiplied by some weight. That is, the fraction is multiplied by the difference of these two weights in the additive notation. Okay? So we can state that this function is B semi-invariant, and this is all we need. So we deduced that for the eigenweight of this function, for any k, the eigenweight of this function satisfies these inequalities. In other words, this means that this eigenweight sits in the dual cone C check, and of course it is the lattice vector. It sits in this semigroup. But we know that the semigroup of lattice vectors in C check is generated by lambda 1, lambda n. This means that nu k can be represented as the sum of the following form. Say d1 lambda 1 plus etc. plus dn lambda n, where all these di's, or maybe dj's, I don't know, dj's, are non-negative integers. Okay? For the function f nu k, this means that the function f nu k is represented as a product f lambda 1 to the power d1, etc., f lambda k, f lambda n, sorry, to the power dn, well, up to a scalar multiple, but let me skip the scalar multiple. We can normalize the functions f lambda 1, f lambda n in such a way that the multiple
f lambda I is a rational function, right?
Say it again.
F lambda I is a rational function, right? Oh.
Well, these functions are rational functions on the open G orbit. So these are these functions. These are these functions. They are rational functions on the open G orbit, but they are actually regular functions on x0. They will show to be rational functions, regular function on x0. But so far they are yeah, just because they may have poles only along these divisors. Okay, so so we have this equality for functions, and finally we get that this function f nu k can be expressed in the following form: s1 to the power d1 times etc. times sn to the power dn over s0 to the power d1 plus etc. plus dn. We have this formula for f nu k.
I think f lambda 1 does not equal to s1 quotient s0.
It is just by definition. Just look at here. Okay.
Yes.
Okay. So we have this presentation for these functions actually. Well, we would like to conclude that the numerator of this fraction coincides with the numerator of this fraction, and the denominator coincides with this denominator. Of course, we cannot do it we cannot state this very thing explicitly. But without loss of generality, let me write down here, with generality, we may assume that this d, this power d, is greater or equal than the sum d1 plus etc. plus dn. So here we use this finiteness, which we discussed in the formulation of the claim. Here we use this finiteness because let me trace back the proof. So what we did here. So we have chosen a function f. We have chosen a function f in this set, which is regular on the open B orbit, and which satisfies these finitely many inequalities. Okay. Then we represented this function in this form, and we computed. How to say? So yes, I mean. So what I want to see. Well, maybe so far we do not yet need this finiteness. Let me just say that.
Professor, I mean, di depends on k, right?
Say it again. Di
depends on k. Because
of course, yes. Of course. DJs, well, better to say DJs, like here, depends on k because they depend on new k, and new k depends on k.
So the d is greater than d. The sum dj, has to be satisfied for all k, right?
Exactly. Of course, for all k. For all k, you are right, but there are finitely many of these k's because we are analyzing a given function f, and it decomposes. So it is represented in this form, yeah, and this f big decomposes as a sum of finitely many of f k's. So everything is finite here, and since there are finitely many such sums, we can choose d to be greater or equal than each of these sums. And when we increase d, this means just that we multiply the numerator and the denominator with some extra power of s naught. So we can multiply the numerator and denominator of these fractions by s naught to some power, to some extra power, and we can increase d by this multiplication. So it is there is no loss of generality in assuming that d is greater or equal than all these sums. But if it is so, then let me come back here. Then we can multiply. So let's compare this fraction and this fraction. These two fractions are equal. They give one and the same function. If you multiply both fractions with the denominator of this fraction with s naught to the power d, then we get that f mu k will be equal to the following: s naught to the power d minus d1 minus etc. minus dn times s1 to d1 etc. sn to the dn. Okay, and all the powers here are non-negative. All the powers here are non-negative. In other words, we see that this f mu k is in the product space m times etc. times m with d factors. Okay, because the sum of these degrees is d. But if f mu k is in this product space is a G submodule. So this guy is a G submodule in the space of sections of the d power of L. And if this highest weight vector f mu k is in this G submodule, then the whole module spanned by these vectors, by this highest weight vector, the whole simple module spanned by this highest weight vector, this simple module is still contained in the G submodule M product with M d times. So this f sub k is also in this submodule. So this implies that f sub k also belongs to the same G submodule, the d product of M. Okay, and this implies in turn that f itself belongs to this product module. Because f is the sum of fk's. And finally, we get that our function f, which is the ratio big F over S naught to D, to the D. Our function f belongs to M over S naught times etc. times F over S naught D times. Hence, it is contained in the coordinate algebra of X naught, which is generated by all these functions in this product space, in these product spaces. Okay, so we have proved the reverse inclusion, and finally we have proved the claim. Oh, well, this claim was quite technical. So it describes the coordinate algebra in this affine open subset. Yeah. This claim described as the coordinate algebra of this affine open subset X naught, which we defined here as a complement to the hyperplane section in X bar. But this description has an important consequence. So this will be the second step of our proof. Now I see that I will not be able to finish the proof today, but I will make some more steps. So an important consequence is that this X upper naught is normal. And hence, the variety X, which is just the G span of X naught, is also normal. So it is covered by normal open subsets, the G shifts of X naught, and hence it is also normal. Recall that we are constructing X as a simple. We want this X be a simple embedding of my spherical homogeneous space Y naught. And one of the assumptions is normality. So we have to prove that X is normal. And we claim that it is the case. So why X naught is normal? It is actually some piece of commutative algebra. If you look at the description of the coordinate algebra of X naught in this form given by the claim, so this is actually the algebra of functions on something which is smooth on the open B orbit, on this guy, satisfying some inequalities given by valuations. So actually the algebras of this kind are always integrally closed in their fraction fields. This is some standard fact in commutative algebra, but let me prove it for you, because I'm not assuming that you you have deep knowledge of commutative algebra, just basic things. Let me prove it for you. So I want to prove that my affine variety x naught is normal. To this end, I have to prove. So let me write it here. It suffices to prove. That the coordinate algebra of x naught is integrally closed in its fraction field. How we do this? So let us take any rational function on x upper node, which satisfies an integral dependence over the regular functions. So this means that f to some power k plus f1 times f to the power k minus 1 plus etc. plus fk equals to 0, where this f1 fk's are regular functions. Okay? So suppose we have such an integral dependence, then I claim that all the evaluations vi take non-negative values on f. Why so? Because otherwise we would have that the value of vi at f to the k, which is equal to k times vi of f, would be strictly less than k minus 1 times vi of f. And this is less or equal. Less or equal than the value of vi at the sum of all these summands. Maybe, yeah. Okay, let me say like this: less or equal than the value of vi at the sum of f1 times fk minus 1 plus etc. plus fk. Just because the value of the sum of functions is greater or equal than the minimum of the values of the summands, but the values of vi at the factors f1, fk, these guys are non-negative because they are in this coordinate algebra. So in this coordinate algebra, the values are non-negative. Okay. And the values of vi at these powers are greater than the value at this power, because we assume that the value at f is smaller, is negative, is less than 0, So we have that we have this sum, and the value of vi at this summand is smaller than the value of vi at the remaining summand. But then these two summands cannot cancel, cannot give us 0, because they have different values of vi. Okay, so the value on here is smaller than the value is less than the value on here. This is a contradiction. So this is the contradiction. So we have proved for our f these inequalities. And similarly, absolutely similarly, we have that the value of the valuation VD corresponding the value of the valuation VD at f is non-negative for any D for any G stable for any prime divisor in my spherical homogeneous space except for D1 dt, because again, so the same argument. If this value were negative, if this value were negative, then we would have that the value of VD at this summand would be smaller, would be less than the value of VD at this sum, because here on this F1 Fk, the value of VD is non-negative because of these inequalities, and because of that F is regular on the open B orbit. So it has the poles of F can be only bistable, only colors. Okay. So and therefore we conclude that F belongs to the coordinate algebra of X0, because it satisfies all inequalities in terms of.
Well, how can we conclude that F is regular on Y upper node, since this is
because all this F1 Fk, all these F1 Fk are regular on Y upper node, right?
Yes.
And if F were not regular on Y upper node, if F were not regular on here, then it would have pole. It would have a pole along a divisor intersecting Y upper node, right? It
yes.
would have pole. It would have pole along a divisor intersecting Y upper node.
Yes.
But here we observed that F does not have a pole along any divisor on our homogeneous space except for these divisors. So this line, the proof of this line is the same as the proof of this statement.
I mean, I mean, so we can use the
So let me draw a picture, so maybe it would be clear. So we have this G orbit Y lower node. We have a B orbit, an open B orbit in here. Y upper node, and we have the colors. Some of them are not intersecting this open. No, excuse me.
Colors never intersect.
All colors, yeah. You are right. All colors are in the complement. All colors are in the complement of Y upper node. All colors are in the complement. So some of them are in this set, some of them are in this set, some of them are in the set B, which is complementary. So B and this set are complementary sets of colors. Some of them are in B, some of them are in this set. But anyway, so what I wanted to what I want to say, I want to say that if my function
for divider, if the divider intersects y naught, then fi, the order of fi at y at the divisor is not negative.
Yeah, if the divisor intersects y naught, then it is not a color first. It is not B stable. And if a divisor intersects y naught, it does not coincide with any of these divisors, and therefore, by this computation, the vanishing order of f along this divisor, D, is non-negative. So it has no poles along D. F has no poles along D. And since f has no poles along any divisor intersecting y naught, it is regular on y naught. So that's all. Did I answer? So
yes,
we get this condition. Okay. So finally we get that what did we prove? We proved that if a rational function over y naught over x naught satisfies an integral dependence over regular functions, then this function is indeed regular. Then this function is in fact regular. Therefore, the algebra of regular functions of x upper naught is integrally closed. In the field of rational functions. And this implies, of course, that x upper naught is normal. So we have to stop. Let me summarize what we have done in the course of the proof. So I presented you a construction. Of a simple embedding with a given colored cone, given by this formula. But I didn't yet prove that this X is indeed a desired simple embedding. We have only started to prove this. We have proved that the affine open subset X upper naught, whose G shifts cover X, this affine open subset is normal, and therefore X is also normal. What remains to prove is that this map phi from y naught to X is indeed an embedding. This I already mentioned. There was a question about this, and I already mentioned that this is true. We have to prove that this map phi from y naught to here is an embedding. That X is simple. That X contains a unique closed G orbit, and that the colored cone of X is exactly the cone we started with, namely this cone. This remains to be proven, and this we'll do on Wednesday. So thank you for your attention, and let's stop now. If you have questions, if you still have questions, then please ask your questions.
Question about the extension of G invariant valuation to a larger field.
Okay, let's come back somewhere, I guess. Well, the first occurrence of this extension was here. So what is your question?
I mean, in which lecture did we talk about this? I did not find.
Well, let me trace it back. Let me try. I think it was. Let me try here, because I do not remember exactly. Was it here? No, it was even before. Maybe here.
I mean, the two approximation theorem did not talk about the extension. Right?
No. This is not well. Just a moment. excuse me, I'm just trying to trace it in my previous lectures. So well, I mean, how to say, maybe I didn't formulate it explicitly as a lemma, but for instance, so what is this lecture? This is, sorry, this is lecture 10. If you open the notes of lecture 10, then you will see this this construction. So we are starting with a field of rational functions on a spherical homogeneous space Y naught. Here, yeah. We take so this Y naught check, it is a cone over Y naught. So Y naught was embedded in a projective space, and Y naught hat, not check. Y naught hat is a cone over Y naught. It is already in the vector space, so the picture is here, yeah. And we have this bigger field. And here on this page, we explained how to extend evaluation from this field to this field. But even more so, if we have a G-invariant valuation, maybe here I should write that it is G-invariant. I don't see. So I missed it somewhere.
This approximate element did not require that V, the initial V.
Yeah. You are right. This approximation lemma is not about extension, indeed. But what we do, we start from a G-invariant valuation here. This V is a G-invariant valuation here. We extend it to evaluation here, not necessarily invariant. So this V hat is not necessarily invariant. But after that, we apply this.
I mean, how does this extension always exist for arbitrary field? I mean, in this case, we have the Y naught hat is degree 1 transcendental.
Exactly. Yes. Formally, yeah. Let me answer.
Field extensions, I don't think we can.
I understand your question. You are right. Formally, you are right that this construction does not explain how to extend evaluation to any bigger field. But what we are interested in, the fields of this form. So we have, excuse me, where do we have this? Yeah. We have the field to which we want to extend evaluation is the fraction field of this algebra as I said, actually, this is one and the same field. It is an exercise for you.
Well, if they are the same field, then we can do the extension. But I want to know how to extend to the fraction field of the right-hand side without proving that they have the same.
Okay, fraction. No problem. Yeah, no problem. It is possible to do it like this. So, you may choose. Actually, it is already chosen. You may take this section S naught. Yeah, this section S naught, and I claim that the fraction field of this algebra is a pure transcendental extension of the fraction field of the field of rational functions on X bar, which is a subfield in this. So let me again recall the construction. You have a map from here to here, and this means that you have an inclusion of the rational functions in here to the rational functions in here. Yeah. So the field of rational functions on X bar, is a subfield in here. And the fraction field of this algebra is a pure transcendental extension of the field of rational functions on X bar. Let me write it here. Maybe it would be instructive because I say everything in words and it is hard to grasp. So we have this kind of inclusions. So we have k of y naught, which contains k of x bar, which is contained in the fraction field of this guy. And this fraction field is a pure transcendental extension of this field by adding the section S naught.
Oh, I see.
So basically, it is the same thing as we considered at lecture 10. It is the same thing as we considered in here. Yeah. So this T will be just S naught. And we can perform this construction.
This is the same as proving the fraction field of the left and the right hand side is the same because the original functions are x bar hat is the unique one dimension transcendental extension.
Yes, absolutely. So if you know if you have this kind of extension, so let me finish to answer your question. If you have this kind of extension, then you can extend a G invariant valuation on here to evaluation on here, not necessarily invariant. But after that, you apply this approximation limit.
I know.
And replace it. Yeah.
I just want to ask about the evaluation. The modify of the valuation to a G invariant one is not a problem.
Yeah. Well, maybe I should formulate this kind of technical lemmas in a more rigorous way to specify exactly which kind of field extensions we may consider here and so on. But why I didn't this at that point?
So I want to ask, if for arbitrary field extensions, do the same method apply?
Well, yes. Actually, you can do the same for an arbitrary field extension, but it is the argument is essentially the same, but more delicate. You can I can give you a reference for this kind of things. Maybe I should even give such kind of reference even before, but you can find let me give you a reference. So you can find a discussion of invariant valuations in a survey paper or survey book, if you like, by myself. So let me give you a reference. It is a book entitled Homogeneous Spaces and Equivariant Embeddings. In Springer Encyclopedia of Mathematical Sciences. Of 2011. And there is a chapter about invariant valuations in this book, so you can consult this book for these questions you are interested in. We discuss how to, in this chapter, we discuss how to extend invariant valuations to arbitrary bigger fields and so on. but this is more technical, so I don't need it for my purposes, and therefore I try to make the exposition as simple as possible. Unfortunately, even still, it remains somewhat technical. So the proof of this theorem is quite technical and long. But if I did it in bigger generality, then it would be even longer. So I don't want to do it. Okay.
So the theorem is that if we have a field extension of F inside K inside L and a group G acting on L, such as G is the automorphism of K and G is the identity on F, then we can extend the valuation on K to the valuation on L.
Well, I would say that if you have a field extension, if I understood you well, then if you have a field extension like this, so K is contained in L, and G acts on both fields compatibly, so G acts on here and G acts on here, then you can extend evaluation on K to evaluation on L. If V were G invariant, then V tilde would be G invariant. But so you have to be careful because these actions of G and on K and L should come from actions on algebraic varieties. So this K should be the function field of an algebraic variety, say X. And this L should be a function field of another algebraic variety, X prime, such that G acts on both X and X prime.
Well, for arbitrary G, K, L, this theorem is not true.
Well, let me finish. I didn't yet finish. So, both varieties should be equipped with an action of G. And the inclusion of fields, K included in L, should come from a G equivariant map from X prime to X. And also, if you do not assume sphericality, so let me remind that I am always considering spherical case. But if you do not assume sphericality, then these valuations should be what is called geometric valuations. They should correspond to some divisors in some modifications of X or X bar. So these things are more technical and more complicated. So if we have a geometric valuation, let me say, well, actually, I think that it is not necessary.
I'm asking if the extension of valuation is pure algebraic, not irrelevant about algebraic group, the theory of algebraic groups.
So you are not interested in the action of G. So what is your question?
I mean, is the extension of valuation independent of the theory of algebraic groups?
Well,
because the field extension and the valuation extension also happens in Galois theory.
If you are not interested in G invariance, then of course you may discard the action of algebraic groups.
I mean, I'm interested in G invariant, but I am not interested in G is an algebraic group. I mean, G can be any group.
Okay. So you mean that if G is any group acting on the field by automorphisms, yeah, like this?
Yes, I mean the extension is still exists or does not exist.
Well, this I don't know. Well, if you do not impose any assumptions on this action, I don't know whether such a general theorem is true or not. So your setting is like this. You have an inclusion of fields. You have a compatible action of some group G on both fields, yeah? So G acts on here, and And you have a G invariant valuation on here, and your question is whether it is possible to extend it to a G invariant valuation on here. Well,
Yes.
I don't think that it is true in this generality. Because our extension procedure use the approximation lemma, and the first approximation lemma, and this approximation lemma relies on properties of algebraic group actions. I can come back to its proof if you want, but you can see that we use some properties of algebraic group actions in.
Yes, I see.
Mm-hmm. So I don't think that this theorem holds in this big generality. Maybe, well, I don't think it's true, but I have no counterexample at hand, but I think that such a counterexample can be easily cooked up. Maybe even you can do it. So actually my interest is in geometric questions related to algebraic group actions. So all things in commutative algebra, for instance, which I use, have this geometric flavor. I do not want to discuss it in bigger generality than I need, because it is dangerous.
No, then I will ask a question. Is this theorem still true if G is not reductive?
If G is not reductive, yes, I think so. Because if you look at the proof, then you will see that reductivity is not essential. Yeah, I think that at this point, yeah, for this extension theorem, it is true, even if G were not reductive. But I think that G should be connected. By the way, you can find, I think that if you look at this book, then
thanks for it.
You will find, maybe you will find answers to some of your questions. Okay. By the way, I should give you some references for the theory of spherical varieties and around, because so far I gave you only references to basic things in algebraic geometry and algebraic group theory and so on. Maybe I will do it on the next lecture. I don't want to spend more of your time now. But this is one of these references. You can find some material about spherical varieties in this book, which is of more general scope. And it is not maybe for the first reading. It is rather a reference book for experts. But still, I mean, with some effort, you can extract many things about spherical varieties from this book, which I explained in my lectures on a simpler level. Okay, so more questions, comments? Thank you for your questions. Your questions are always welcome, because when you ask something, I see what I am missing or what I am explaining not clearly. So please ask questions at any time. This is a good idea to go through the material to ask questions. Well, if there are no more questions, then maybe I'll stop sharing. And see you all on Wednesday. So, see you on Wednesday. Goodbye.